signal noise issues are some of the biggest issues that we have in EEG. EEG is probably the noisiest of all the different brain imaging techniques that we have. So it's really important to understand the different sources of noise and how we can deal with them. And our remote's not working now. Broadly speaking, we can define noise in EEG as anything that's not the brain. Oh, sorry. So this includes things like electronics in the room, like the monitors we're using, power cords. One thing I've seen quite dramatically is you have to be very careful about how you route the power cords in your EEG testing room. If they're, say, going under the desk that the person's sitting at and they stick their foot out and their foot's touching or near the electrical power cord, you'll see a huge increase in noise in the signal, because even though they're not being electrocuted, there's this effect that's called the right-hand rule, or Ampere's circuital law, which basically says that anytime you have a current flowing, it induces a magnetic field around it, and anytime you have such a magnetic field, it'll actually induce a current in another conductor that's nearby. So where you've got current flowing through that electrical power cord, it's creating a magnetic field. You put your foot into that magnetic field, and that'll induce current in your body. Now, it's not going to be enough current to electrocute you, but it's enough that we'll be able to pick it up with EEG electrodes. And relative to the size of your brain, they're quite noticeable components. Head movement is another one. And this isn't so much, there are issues around the muscles, especially in your face. So if there's muscle activity under or near the electrodes, that's going to get picked up. That's more if you like scrunch your face up, or if you're talking or doing stuff with your face, you'll pick up those muscle artifacts. The bigger issue with head movement is that, again, this right-hand rule, if we start moving an electrical conductor like the wires that are carrying these EEG signals to the amplifier, if we move them through a magnetic field, which is basically any environment that you're in where you're near electronic devices, they're radiating out these magnetic fields. So if you're moving the conductors through those fields, you're going to induce currents in those conductors. And so you're going to get all these extra currents in the wires just because the wires are moving around in the environment. So that can be a problem. Muscle I already talked about. Relatively rarely with EEG you can pick up EKG, so electrocardiogram. My experience is that's typically with people who are overweight for whatever reason, whether it's the high blood pressure or something. In most people, in my experience that we've tested in the lab, we don't have that issue. If you do have it, you can see, it looks more like this one on the right, not the one on the left. But there's kind of a distinctive EKG signal, and you'll see these little crisp spikes throughout the data. They're not so much of an issue because, again, we're recording lots of trials, averaging them together, and those EKG signals aren't going to be time-locked to your signal or to your stimuli, and so they're going to basically just sort of average out over time. Some of the other sources of noise are worse just because, whereas that signal is very quick and transient, and occurs at different points in time. Something like if you start scrunching your muscles, as long as you're contracting that muscle, you've got this oscillating frequency pattern that will be picked up in your electrodes. And if you've got muscle activity on lots of trials because the person's tense or they're like squinting at the screen or something like that, it's not necessarily going to average out across trials because it's present on lots of, if not all, the trials. So it is important to try and minimize those things as much as you can, even though there are ways of dealing with them later. Another one is sweat. Extreme example illustrated there. Hopefully nobody in your EEG experiment is sweating that profusely. But even just wearing the EEG cap, your head might get warm, and it might start to perspire a little bit. And that changes the conductivity, it increases the conductivity of your skin, because now you've got this saline solution, basically, sweat, on there. And even in low concentrations, that's going to mean that more electrical current is able to flow sort of across the scalp and interfere and get picked up in your electrodes. And that typically, so the sweating typically manifests as what we call skin potentials, which are these very slowly changing drifts over time. So your ongoing EEG is sort of this rapidly changing stuff. then sort of riding under that is this broader, slower change that's typically related to skin potentials. The best way to deal with that is to cool the person off and lowering the impedance. Sometimes it's not so much the person's sweating too much as the impedance on the electrodes is not low enough, and so just reducing the impedance can help a lot. So if you take all of this together, the ideal situation for recording EEG is, well, ideally like some forest where the person's very super relaxed and there's no ambient electronic noise other than your EEG system. But in practical terms, it's like in a room where you've minimized the amount of electrical stuff. The other nice thing is magnetic fields drop off sharply with distance, with the square root of distance. And that means that, you know, putting your foot right on one of those power cords is going to give you a lot of noise. Moving your foot even a few inches away is going to dramatically reduce the amount of noise. So you don't have to worry about trying to isolate your subject from everything within the room. You just need to make sure everything's reasonably far from people and that they're not like sticking their feet out or reaching out and touching stuff and doing stuff like that. You also want them to be as relaxed as possible to minimize the muscle tension, not so relaxed that they fall asleep. So there's sort of a fine line there. In my lab, we try and seat them in a chair that's not super uncomfortable, but not super comfortable, and also give people frequent breaks where we offer them like chocolate and caffeine and stuff like that to help keep them awake and alert. Minimize head movement and eye blinks. We haven't got to that, but minimize eye movements. I'll come back to that one. Studies requiring people to move. Well, it's, if you're moving your arm, that's probably okay. But if there's even a lot of shoulder stuff in there, that can translate into neck muscle activity, which can get picked up. So trying to minimize the kinds of movements. If you're having people make responses, it's ideal if they're just sort of holding some sort of button box or gamepad or something, rather than having them make reaching movements unless they have to. A lot of stuff like that. If you're having people make vocal responses, the ideal thing is to design your experiment in such a way that, and keeping in mind that all of the ERPs that we're interested in probably occur within the first second or even half second after you see a stimulus. And so if you do things like delaying when the person has to make a response, so they see the stimulus, there's a little pause, then they get some little prompt that says, okay, now press the button. That helps isolate things. If it's a vocal response, same thing. Delay the onset of that vocal response till after that critical window when you want to be looking at the EEG, then you should be okay. I already talked about the right-hand rule, talked about it a lot in the book. That's just an illustration of it. This is what it looks like when you're actually like touching those wires or otherwise getting electrical line noise from electronic devices in the environment. And it's pretty distinctive because our power is alternating current at 60 hertz, which means that what's flowing through any power cord is oscillating between positive and negative 60 times a second. This is pretty high frequency compared to most human EEG, which is generally sort of 30 hertz and below. There is human stuff above that, but usually it's not a focus in an experiment, certainly not in an ERP experiment. And so here you can see the unfiltered data. So this is the electrical line noise. This is sort of high frequency, rapidly changing stuff. Even when you've got other, like halfway down here on the left, you can see some more sort of clearly EEG, some slower changing stuff, but the higher frequency stuff is riding on top of that. This is now where we've filtered out, so removed the 60 hertz noise. And you can see things, a lot of the other features, the slower changing features are still present in the data, but that higher frequency 60 hertz line noise is filtered out. So this is the other thing, is there's some stuff that you can remove after the fact through steps like filtering. Let's talk the chapter, we'll talk more about it in the labs. But as much as you can do to get clean data at the outset is great, because sometimes the line noise can be really big and can be a little harder to remove. And also when you're recording the data, it's nice to have relatively clean data to look at, so that you can tell when an electrode, if the impedance starts going wonky or it gets noisy because the person's got some muscle tension. So sometimes over time, somebody's doing an experiment, their neck starts to get sore, or they start to move a little bit. It's nice to know that, okay, that's muscle tension. We can see that because there's not too much other noise in the data. So it's still worth keeping it clean. This is not how to deal with electrical noise. tinfoil hats do not protect you from anything. But as I mentioned, there are ways of dealing with it. So beyond just this sort of controlling your environment, trying to keep things away from people, another approach is to use what's called a Faraday cage, which is basically an environment, some sort of cage or a box or something like what you see here on the right, that's conductive, and it's connected to an electrical ground, so literally sort of into the earth. And basically that, the way it works is all those magnetic fields that are impinging on it from the outside induce current in the Faraday cage, and it gets shunted into the ground, and it doesn't transmit through the cage. It basically just all sort of gets captured and shunted away. This is an extreme example, again, where you've got this thing that's generating huge electrical currents, and the guy is completely safe because everything's been shunted by the Faraday cage. Faraday cages can do a good job of keeping outside electromagnetic noise out of your booth. They don't do anything to remove any noise that's occurring inside the booth. And this is why they're, again, sort of the old school thinking was important. The new school thinking is that because these magnetic fields drop off sharply with distance, in most environments, there aren't a lot of things that are generating electromagnetic fields that are so big outside of your EEG room that they're actually going to result in a big artifact inside. Mostly you're dealing with artifacts that are coming from the stuff that has to be in the room anyway, like the computer screen, other electronic devices that might be present, and that's pretty much it. The other thing is any wire that's coming into that room. With a Faraday cage, there are ways of having fancy connectors that filter out things that are coming in. But if you just run a power cord to your monitor inside the Faraday cage, you've basically defeated the purpose of the Faraday cage, because that wire as it's coming in is also a conductor. It basically acts as an antenna, so any other ambient electromagnetic noise in the environment is going to induce its current in that wire. That's going to be brought into the booth, and it doesn't really matter if you've got a fancy, expensive Faraday cage around the booth. You've basically sort of circumvented that, and you've brought this artifact in. So it's like you can either spend a lot of money to minimize the signal that you can otherwise take care of by filtering for the most part, or you can just control your environment as well as possible and do some post-processing afterwards. It's not universally the case, and I've known people who, just through basically bad luck, had their ERP systems in situations like in hospitals or something where there happened to be big medical equipment around that did generate big electromagnetic noise. And it wasn't necessarily this really clean 60 hertz stuff. It's kind of like stuff that was oscillating over lower frequencies, or that was on only at certain times of the day and made the noise much bigger than it would otherwise be. So there's situations where the Faraday cage can be really useful, but it's not universally required by any stretch of the imagination. So in my lab, I have one of these, and then I have two other EEG systems that are just in average rooms without that kind of shielding, and the data are, just as good from any of them. And in the booth where you're going to be doing your recordings, you'll also see that it's a Faraday cage. It's actually a homemade one. It was apparently built by a professor here at Dal many, many years ago, before my time. But it's a very well-built Faraday cage. It looks like crap. They put like those old sort of cardboard tiles all over it, but it's engineered very well. And you'll notice that especially like the door itself is very heavy, and it's got this big, sort of intimidating looking big lever that you use to close it, because it's like solid copper. Okay, so Faraday cages. I've harped on the importance of getting low impedance between your electrode and the scalp already. This is just reinforcing that and adding on something that I hadn't mentioned before. Right, so the basic principle is high impedance, then you have a worse path for current to flow from the brain, basically scalp electrode. And then the other side of that coin is if you have less EEG getting into your wires, you're going to have proportionately more noise, typically. And the stuff that's coming, if you don't have good impedance, low impedance between the electrode and the scalp, those skin potentials, muscle potentials, the 60 hertz noise from the environment, those are all going to be relatively bigger. because everything's about this signal-to-noise ratio. So the noise in the environment, you can kind of control your environment, but once you've controlled it, you have sort of some baseline level of noise, and that's going to get picked up. And so then it's how strong can we get the EEG signal relative to that baseline level of noise. So the lower we get the impedance, the more we're going to sort of improve our signal-to-noise ratio by boosting the amount of signal, noise being sort of the constant. The other issue is that if your impedances aren't really consistent across the scalp, then you're going to have this mismatched impedances and decreased common mode rejection. So again, common mode rejection is this active minus ground, reference minus ground. And so if you don't have good low impedance at the reference and the ground, you're going to have bad common mode rejection because you're not going to be able to sort of subtract out all the background noise that the reference and the ground are picking up. And then if you have different impedances, wildly different impedances, at least at different active electrodes, then, even if the ground and the reference are good, the ones that have the active electrodes that have high impedance are going to give you worse data. And that means that when you're looking at, say, one of those scalp maps, right, you'll have from electrode to electrode, you might have sort of better signal to noise at one, worse at another, and you're going to get these weird distributions where the scalp distribution of the electrical potentials, there's the brain stuff in there, which is nice and big and smooth, but then there's like each individual electrode might be more noisy or less noisy, and that's going to introduce some noise that changes more quickly across the scalp. And so that's actually a good hallmark. Once you've got your data from a subject, you average your trials together, look at it. If it looks like these nice sort of big, smooth, slowly changing potentials across the scalp, that's pretty good data. If it looks like you've got a lot of really fine-grained stuff going on, that's probably because you've got a lot of noise and maybe mismatched impedances at different electrodes. And so that's you don't get that nice, smooth representation of the brain activity. All right. So to lower impedance, I've talked a lot about the importance of it. The physical act of doing it is put the gel in, electrode, rub the gel around. I meant to bring caps today, but you'll see the caps eventually. But you imagine the cap is basically got like a plastic ring that's hollow that you plug the electrode into, or the electrode's sewn into it, and it's got a hole for the gel to go in. And so you've got a gap between the electrode and the scalp, and you want to fill that gap with gel. So you sort of squirt some gel in and make sure that you have an actual physical connection of the gel between the scalp and the electrode, and then you want to start massaging the gel into the scalp to really sort of work it into the pores and get a good quality connection. In doing that, typically we use a blunt syringe. Sometimes people also have these blunt wooden sticks to do it. And as well as massaging the gel in, as you're rubbing the scalp, you're actually removing that outer layer of dead skin cells, which also helps to get a good connection. And so a lot of lowering impedance is you do this, and then you measure the impedance at all the electrodes, and the ones that are high, you go in and you keep working on those electrodes and really sort of trying to rub the gel in. You have to find the sort of sweet spot between actually causing injury, because you don't want people to say ow, but you want to be relatively firm and actually be sort of scraping those dead skin cells off. We tend to avoid terms like poke and scrape when we're actually talking to research participants. We use words like massage and rub, but in principle you have to think about the physical, mechanical sorts of things that you're doing there. As well, some of the points here, so the scalp and skin should be clean. So normally we'll tell people, the morning before you come in for EEG, please wash your hair and don't use any leave-in conditioner or styling products because those will interfere with our getting good impedances. And by having a clean scalp, they've already abraded their scalp and removed a lot of the oils and dead skin cells and so on. So your sort of best case scenario there. Any spots where there is no hair, you can clean that with rubbing alcohol, or we've got this stuff called New Prep, which is kind of an exfoliant, so it's got some rough stuff in it. And again, that'll help remove oils, dead skin cells, stuff like that. So forehead, typically we put electrodes around the eyes to monitor for blinks and eye movements. So again, exposed skin, you can clean that, and then the mastoids behind the ears, if you're putting electrodes there, that's another good place you can clean, especially if you think about like the reference electrode and the importance of having good low impedance at the reference and ground electrodes. if those are going to be on bare skin spots like the mastoids, then it's really ideal to keep those super clean. All right. Yes, and this word twiddling is often used to describe the act of lowering the impedance. And then I've mentioned the ocular, so the eye movements and eye blink effects. This is what they look like in your recordings. So if you see, we've got ongoing EEG from however many electrodes, and then at certain points you've got these really big deflections, like this one that's marked as a blink, this one that's marked as a blink. So you can see, compared to sort of the peak to trough amplitude of the ongoing EEG, when you get a blink, it's like 10 or more times bigger than your typical ongoing EEG. And what's going on there is when you blink, you close your eye, you've got a new path for current to flow, because current can sort of flow across your eyelid that didn't exist before. And if you think if there's kind of a steady state of all the electromagnetic stuff hitting your head and being conducted and so on, by blinking, you're changing that current path very briefly, and that's why you get those big deviations. So it's not necessarily muscle activity, it's actually this current path change. The other thing is, if you think about the anatomy of the eye, you've got this big fluid-filled sphere, and you've got a retina at the back of the eye. And the retina has lots of cells. Those neurons are electrical, and so your eyeballs are actually dipoles, electrical dipoles, particularly across the retina. But again, that conducts through the nice wet material of your eye. And so as your eyes move around and point in different directions, the orientation of those dipoles is going to change with the position of the eye. And so if people move their eyes side to side, up and down, anything like that, that's going to cause big deflections in your EEG as well, because you have these dipoles that are moving around. And this is actually important both in recognizing, so the eye movement's a little less clear here, but if you look down at the bottom, the second from the bottom especially, you can see a little sort of square plateau there. So usually what happens, that's when somebody looks, say, to the left and then back to center. So as it goes up, that's looking to one side, sort of flat as long as they're looking there, and then it drops back down when they move back to center. And so in terms of thinking about experimental design, the ideal EEG experimental design will not involve eye movements. It involves presenting whatever you want people to be looking at the center of the screen. So for things like we're having people read sentences, we don't print the whole sentence on the screen for two reasons. One being that they'll have to move their eyes, and the other being that as they're moving their eyes from one word to the other, you don't actually know when they see each word, right? So in terms of thinking about the time locking, all you know is we know when the sentence came on, but we don't know when they read the third word in that sentence. So in a sentence processing experiment, we'll use what we call RSVP, or Rapid Serial Visual Presentation, which is just presenting each word in the center of the screen, one after the other. And so they don't have to move their eyes, and we know the onset of each individual word in the study quite well. So anything like that. Another thing that's sometimes done, especially where like visual attention studies or something, where it's really important that you know, say you're looking at peripheral visual attention, so you want somebody to fixate on the center of the screen and you're presenting stimuli out on the sides. And it's important that they're actually processing those stimuli as peripheral stimuli and not just looking at them. And so people monitor eye movements in those experiments. And often what they'll do is they'll actually have an online eye movement detection algorithm running on the computer. And when it detects an eye movement, it'll mark the trial as bad in the EEG study and tell the stimulus program to actually add another trial to the experiment so that you're sure that you get the target number of trials, because any ones where they move their eyes, even though post hoc, as we'll talk about in the lab and mentioned in the chapter, there are ways of removing these eye movements or correcting for them. If the point of the experiment was you're supposed to be looking there, as soon as they look over, it doesn't really matter that you can correct for that eye movement. They're not looking at the right thing. And so from a sort of conceptual point of view, the assumptions of the experiment are not being held. And so marking those trials online and being able to place them is really valuable. And this is where we end, is there's a lot of what we'll focus on in the labs and so on is once you've collected the data is working with the data and cleaning the data up, all these different algorithms to correct for eye blinks and filter data and so on. But there's no substitute for good data. So the cleaner your data is going in, the happier you're going to be. All of these techniques that we have for signal processing only work kind of. And so, if you get noisy data, then all the processing in the world is going to make it a little less noisy, but it's not going to make it good data. So everything that you can do, and this is, I think, something that has to be emphasized over and over again, because it's very easy to think, okay, we stick the electrode cap on, we squirt gel in, we get those impedance measures. As long as the impedance measures are fine, stick them in the experiment, go, and they're good for half an hour. We can go have a coffee and talk and hang out. No, you should be monitoring those EEG electrodes the whole time. Look at the data, because the data will tend to get noisier. People get bored. They start moving around. They're maybe blinking a lot. All of that stuff is stuff that if you're monitoring the electrodes, you can say, okay, it looks like they're getting restless, or it looks like they've got some muscle tension. We're seeing more high-frequency muscle noise. So let's pause the experiment, go in and actually talk to the person and say, hey, do you want a break? Or, hey, it looks like you've got some muscle tension. And often, like, the neck stuff, which typically gets picked up kind of around the ears and stuff like that, you'll see this noise arise, and just telling somebody you've got some neck tension, can you just try and relax? And that's enough for the data to get a lot better. Or they're blinking a lot, you just say, hey, you're blinking a lot, do you want to take a break, or can you try and just blink between trials rather than during the trials? There's a lot you can do to improve the quality of the data through stuff like that. And also, if an electrode looks noisy, maybe you go in, you add a bit of gel, you twiddle it a bit more, and get a better connection. So sometimes even when the impedance number looks okay, the data might not look okay, and working with the electrode will actually benefit that. So it becomes a real, there's an art side to acquiring EEG data, maybe more than other neuroimaging techniques, as well as sort of basic technique and the science side. So yeah, that's what I got for today.